Welcome to The Explainer. Today, we're diving straight into a fascinating 14-step roadmap by ZeroX Moves that completely changed how I think about AI agents. If you've ever felt like your agents are just taking way too long, getting easily confused, or totally dropping the ball on complex multi-step tasks, well, you're in exactly the right place. We're going to explore how to shift from the old, slow way of interacting with AI, typing a single prompt and just waiting, to engineering highly sophisticated multi-agent fleets.
Right off the bat, think about this wild statistic from the source. 9 out of 10 developers are building multi-step agents where half the steps are needlessly waiting in a single file queue. It's crazy. Step 1 runs, and then Step 2 just politely waits for Step 1 to finish, even if it has absolutely no reason to. Then Step 3 waits for Step 2. They don't route, they don't branch out, and they certainly aren't parallelizing anything. They just stand in line. And this creates a massive bottleneck. Your one context window eventually fills up, and suddenly the agent forgets what it was even doing in the first place.
So here is our agenda for today. 1. The linear agent trap. 2. Nodes, edges, and contracts. 3. Fan out and fan in. 4. Verification and routing. And 5. Real-world graph topologies. Let's get into it.
Section 1. The linear agent trap. Escaping the degenerate graph.
The source points out something kind of mind-blowing here. A linear script is essentially a degenerate graph. What that means is it has absolutely zero redundancy. If you've ever written a prompt that says do A, then B, then C, you've accidentally built a super fragile, unbranching chain. If Step C stalls out, Step D literally never happens, and all the hard work from Step A is just trapped in limbo. But by shifting to an agent graph, you slice right through those unnecessary queues. You start asking, hey, which of these tasks can happen at the same time? And that simple shift turns your fragile chain into a redundant, lightning-fast fleet of concurrent executions.
Section 2. Nodes, edges, and contracts, defining the primitives.
To actually build these fleets, we have to completely redefine our basic building blocks. In graph engineering, a node isn't just an agent having an open-ended chat. It is a single, bounded job, enforced by a strict schema. Because think about it, you can't parallelize a task if you don't know exactly what it's supposed to do. So, we give every node a strict contract. The input is passed in explicitly. We never just assume it's in the chat history, and the output has to be a specifically defined shape, usually validated using a JSON schema. This means Claude will automatically retry if the output fails, rather than leaving you to manually parse and pray over a wall of free text. And that brings us to edges. The absolute crucial point here is that an edge isn't just code saying and then do this. It only actually exists if data moves from node A to node B. It's a huge perspective shift. For example, if you ask an agent to summarize a file and then tell you the weather, there is no actual edge there. The weather report doesn't consume the summary, right? Those are two completely disconnected nodes that shouldn't be waiting on each other for a second. When you name an edge by the data it actually carries, you can instantly see if the dependency is real or just a bad habit.
Now here is the quiet, beautiful win of graph thinking. Because edges are just JavaScript code carrying shapes between nodes, the coordination itself costs 0 model tokens. Literally 0. A massive amount of what developers usually burn expensive AI tokens on is really just moving data around or flattening lists. In a graph, all that reduction and filtering happens in plain old code. You don't need a heavy AI agent just to move data, which means your entire orchestration layer is basically free.
Moving on to Section 3. Fan out and fan in, the engine of scale.
So how do we build this into an engine that unlocks massive speed? When you have multiple independent sources to check, you fan them out using a parallel function. This lets Claude scale up to hundreds of subagents without drowning the main session context. Instead of forcing one agent to check 10 files one by one, you just spawn one subagent per file. And the genius part is that Claude's main context window never has to hold all those sources at once. Each subagent carries its own tiny, focused context, does its job, and only the final answers come back. You get the combined brain power of 100 agents in a fraction of the time.
Now, topology dictates your latency. The source offers a pretty brutal smell test for this. If you have a transform step in the middle of your workflow that doesn't rely on comparing items to each other, use a pipeline. A parallel function actually creates a barrier, meaning it literally waits for the absolute slowest subagent to finish before the next stage can even start. A pipeline, on the other hand, lets fast items finish early and instantly move to the next stage without idling. Bottom line, don't make everything wait around just because your code looks cleaner that way.
Put those concepts together, and you get the diamond. This is the ultimate workhorse topology of every serious AI graph. It's a three-step process that forms the skeleton of a market scan, a code review, or a massive research report. First, you fan out to gather a huge breadth of information. Then, you use plain, zero-token code to reduce, flatten, and filter that data. Finally, you synthesize by passing that compressed data to a final agent to write the definitive answer. Once you see the diamond pattern, you stop asking how to make your agent do more steps, and you start asking exactly where to split and where to merge.
All right, Section 4, Verification and Routing, Quality Control.
So we're moving fast, but how do we actually ensure quality when dozens of agents are working at once? We definitely don't just want really fast mistakes. The real leverage of a graph is wrapping your nodes in verifiers that try to kill bad findings before they move downstream. The source outlines 3 powerful adversarial patterns. An adversarial verifier spawns independent skeptics specifically designed to refute a finding. It only passes if it survives the attack. A prospective diverse verifier gives each agent a distinct lens, like, say, one checking purely for security, another purely for correctness, because diverse checks catch blind spots. And a judge panel generates multiple attempts, has parallel judges score them, and then synthesizes the absolute best parts of the runners-up.
When it comes to routing edges at runtime, the rule is this: Claude provides the judgment, but plain old code provides the reliability. Imagine you're routing a customer support ticket. The AI agent classifies the ticket, that's the judgment part. But the actual routing down the path to the correct human handler, that is just a JavaScript if-for switch statement based on that validated output. You really don't want to merge in surprises where the AI just randomly decides to skip a security audit because it felt like it. The routing is strict, deterministic code. The decision-making inside the node is AI.
Now, sometimes you just don't know how deep a task will go. Finding one software bug might reveal 3 more, right? For that, you need a cycle. The pattern here is loop until dry. You basically keep spawning finders until a set number of rounds surfaces nothing new. But the source warns about a massive expensive pitfall here. If you don't deduplicate against rejected findings as well, your agents will just excitedly rediscover the exact same dead ends over and over again, burning through your budget in an infinite loop. Always dedupe against everything seen.
Finally, Section 5, Real-World Graph Topologies, the Architect's Playbook.
So how does all this come together in the real world? Whether you are orchestrating a massive code-based security sweep or a broad ecosystem scan, the underlying logic relies on scalable graph topologies that you can implement today. The source maps out 6 specific ones. For instance, in an adversarial diff review, a router checks the size of a code change. If it's tiny, it gets a quick pass. If it's huge, boom, it triggers a full parallel audit, with reviewers looking through distinct security and performance lenses. Or take an ecosystem scan. Claude can check dozens of release blogs and forums in parallel, rank them by impact at a barrier, and write up a neat, comprehensive digest.
Here's a brilliant economic trick for you. Why use your most expensive tokens for boring data extraction? You can use dynamic workflows to route repetitive, low-level extraction nodes to much cheaper models. Not every task requires the smartest, most expensive model on the market, and using a graph structure makes this incredibly obvious. Save your premium tier model specifically for the merge node, where true judgment and synthesis actually happen. This completely flips a token-hungry workflow into a highly economical one without changing the shape of the output at all.
Honestly, this next part blew my mind a little bit. You don't even always have to draw the graph by hand. By using tools like Claude Code's Deep Research, Claude can actually tailor a fleet specifically for the run. By simply describing your objective, Claude acts as the architect. It breaks down the task, chooses the perfect fan-out strategy, spawns the coordinated fleet of subagents, and synthesizes the result. You get a custom-built graph generated dynamically for the exact problem at hand. It is so cool.
And that brings us to the ultimate takeaway from 0x Movas. A prompter asks a question, an architect draws a graph. The linear agent was just the very first shape we all reached for because it mimics how we type. One line, one head, one thing at a time. But once you see your work as nodes and edges, you stop asking an individual agent to try and juggle way more context, and you start asking the graph to run wider. You gate the edges for confidence, and you tier the models for maximum efficiency.
The real ceiling on AI productivity isn't the model itself anymore. It is the shape of your workflow. So what kind of system are you going to build next? Are you going to stay stuck under the ceiling of single-file queues? Or are you finally ready to become an architect, draw the graph, and orchestrate a fleet? Thanks for joining me on this explainer. I hope this gave you a completely new perspective on engineering your AI workflows. See you next time.